I want to find the Taylor series of e to the x and talk just a little bit about what I can do with it once I find it. So the general formula for the Taylor series for a function f of x is the sum of the derivative, the nth derivative evaluated at the center point x equals a over n factorial times x minus a to the n. For e to the x, the most convenient value for me to center my Taylor series at is going to be x equals 0, because the original function evaluated at 0 is 1, and also all of the derivatives evaluated at 0 are going to be 1 also. If I evaluate those derivatives somewhere else, then I'm going to have e raised to some power, which is a little hard to work with. So I'm just going to center it at x equals 0. That means I'm choosing a equals 0. And now, the typical way to go through a Taylor series is to start listing out the derivatives and evaluate them at your center point, and then try to pick up the pattern. I'll go ahead and write it out, but it's a little silly for this one. So first, when you plug in n equals 0, that means the original function. So the 0th derivative is the original function, which is e to the x. If I evaluate that at 0, I get e to the 0, which is 1. The first derivative is also e to the x. I evaluate it at 0, I get 1. And of course, as you already know, this is going to happen for every single derivative. So I can stop writing, but it's hard for me to stop myself. If I go to the nth derivative, I just want to show you what you would do for other functions as well. It's still e to the x. What I'm looking for is a pattern. It was easy to find it for this particular function. So the Taylor series for e to the x is easier than the Taylor series for almost any other function because of this super nice pattern. All of my derivatives evaluated at 0 are equal to 1. So in all of my terms, this numerator is just 1. A is 0. So since I have 1 over n factorial times x to the n, I'm just going to bring that x to the n up in the numerator. That is the Taylor series for e to the x. Let's write out some terms for it. The first term, when you plug in n equals 0, you get x to the 0 is 1. 0 factorial is defined to be 1, so that first constant term is just 1. And then your next term for n equals 1 is x to the 1 over 1. For n equals 2, you get x squared over 2 factorial, which is 2. And then I get x cubed over 3 factorial, which is 6, and so on. The one thing that you may not have much practice with is that this n factorial grows really fast. It grows even faster than the exponential functions. So these denominators are getting small extremely fast. I mean, the denominators are getting big extremely fast. What that's going to do is make this series converge quickly for all values of x. Once I've found this thing, one thing I could do with it is approximate numbers. This is probably the least exciting thing you can do with a series, but it's also the easiest to kind of get your hands on and intuitively understand. So let's talk about that for a second. If I want to find an approximation, for example, for the number e, I can do that by just plugging in x equals 1. So if I plug in x equals 1 into here, I get 1 plus 1 plus 1/2 plus 1/6 plus 1 over 4 factorial. So 4 times 6 is 24. 1 over 5 factorial, and so on. And so to get a taste of why series are so useful, This gives me a lot of power for determining what mixture of energy I want to put in versus accuracy I want to get out. Balancing those out is extremely important for applications of math. If you think of modern technology, maybe you've got a drone flying with a chip in it and it's got to make calculations, lots of calculations, every second. You don't have to get extreme precision out to the millionth decimal place. You have to balance out how much time you want to spend calculating versus how much accuracy you want in your solutions. So for example, if I'm calculating this by hand, maybe all I'm interested in is getting to the nearest hundredth. Then if I add up all of these terms, the next term after this is going to be 120 times 6, 1 over 120 times 6, so that's 1 over 720. And then the next term would be that 1 over this times 7. What's that? 49 and 14, so 50, 40. And so on. This denominator is going to get really big really fast. So if I'm just looking for getting this accurate to within 1/100th, it looks like if I just add those, that will be good. There are ways to be much more precise than just eyeballing it and saying that. That's a very interesting topic for Taylor series. Another interesting thing is thinking about how to integrate new functions involving e to the x. So I'll give you a quick example and then I'll end the video. Let's say I want the integral of something simple, but that I don't know how to do yet, involving e to the x. So let's do e to the x squared. Say I want an expression for that. And maybe I even want to evaluate this for certain numbers. So I'll pick easy numbers to work with. I'll just pick 0 and 1. So e to the x squared is some function. I should be able to integrate it from 0 to 1 because it's continuous and differentiable on that interval. But I don't know how to get an antiderivative of this thing. My new hope, is to rewrite e to the x squared as an infinite series and then plug in the bounds, and then I'll have just fractions like this that I can add up, and then I can just figure out what level of precision I want and cut off everything after that. It turns out getting a series for e to the x squared is pretty simple once I have a series for e to the x. Because, for example, if I want the series for e to the 5, then I just plug in 5 for all of these x's. So if I want the series for e to the x squared, I just plug in x squared for all of these x's. So instead of an x here, I'll have x squared to the n. I think I'll write it like this. Once you get more practice with it, it's probably better to write it like this, but let me write it like this first. So that series becomes 1 plus x squared squared over 2 plus x squared to the third. That's 6 over 6. The next one would be x squared to the fourth over 4 factorial. And I'm wanting to find the antiderivative of that and then plug in the bounds. Now that I can write it like this, it's very easy for me to find the antiderivative term by term. This is a nice fact for these series. So just start taking the antiderivative term by term. I'm not going to write them all down, but I would have x to the fifth over 5 times 2, and so on. I want to go from 0 to 1. Now notice, if I would have written this series out using this expression and replaced x with x squared, it would be pretty easy for me to find the general antiderivative from there, so I could have saved myself a little time. But I think this is nicer to look at for a first example. Now I plug in 1 into this, and I plug in 0. When I plug in 0, everything goes to 0. So I'm just getting whatever I have when I plug in 1. I could carry this out to whatever precision I want, and that's the integral from 0 to 1 of e to the x squared. So this ability to go from a function whose definition is very complicated to an expression where I can just work with polynomial terms is really nice. It allows me to sort of get my hands dirty with this and get good approximations very quickly.